3-3, I gave you a paper that you could use to help you. There's not one new thing on this paper, but what this is reminding you of, things that you know are true from Chapter 2 and older. Like on the Chapter 2 stuff, we had a thing called general formulas. Plus or minus theta, plus 360 Ks and 2 pi Ks and stuff with Ks. We're going to need those, not today, but next lesson. We'll be in 3-3 for 2 days, so this is like 3-3 part 1. When we do 3-3 part 2, you'll need that. If there's negatives thrown in your problems, we got adjustments that we used to make in Chapter 2, whether we made it negative or did 180 minus, there it is. The chart, we will use the chart today, so having a copy of the chart handy is not a bad thing. The old what's positive where, SACT, we'll need that today. So this isn't a bad sheet to have nearby when you're doing your homework and you don't then have to look up old things. By the time you take the test, though, you want those things to have worked their way into your brain if they haven't already. So that's there for you. Tomorrow, not tomorrow in school in calendar terms, but next day I see you in Trig, we're going to do another one of those property quizzes where we're just going to try to memorize some properties. I'll give you the blank sheet like I did last time. So the title is worth a point. The first title are going to be called co-function properties, which you're semi-familiar with already. I'll tell you how. And then there's another group I'm going to call sum and difference properties. But on the paper I gave you, they might be called composite argument. Is that what they're called on there? So whether you call it composite argument or you call it sum and difference properties, I don't really care. Pick a name. If you happen to misplace that paper where you're building all these properties, and I'm assuming you're going to throw these on that paper that's about 30% filled, and after today it'll be about 60% filled. If you happen to ever misplace that paper, all of the properties are going to be published for you in the book on page 102. Page 102 has properties we're going to do and some that we even aren't going to do. And just by way of advertising for the future, when we get to the test, there's going to be a lot of them. And so I don't want the test to be a situation where you mismemorize a property and lose a point, and then do 10 problems using that property and miss 10 more points. Okay? That's a little bit extreme. So when we get to the test on this chapter, page 1 of the test will be you filling in the paper that I can see you're filling in right now, just from your memory. And then you give me that paper, and I give you a copy of page 102. And then when you do the rest of your test, you're working from properties you know are right. So if you make a mistake, you're only going to miss 1 point, not have that snowball out of control. Okay? But I've got some page 102s like run off and ready to go for test purposes. We just trade papers halfway through the test. Co-functions, let's think back to our chart and I'll kind of ease our way into these properties which you sort of know. If you look at the chart, cosine of 30 is the same as sine of somebody else. Who would that be? 60. Cosine of 45 is the same as sine of somebody else. 45. Not on your chart, but seeing if we can sense the trend. Cosine of 20 is not on your chart, but it would be the same as the sine of some other number. 70 is true. What's the relationship between those two numbers? They add to 90. Geometry work. What was add to 90 called? Complementary. That's how this co got its name. That's the complementary function for sine. The complement of sine is cosine. So here's a property. If we have cosine of 90 minus somebody, that's the same as the sine of that somebody. Like 90 minus 70 made 20 a second ago. But if we do a cosine of 90 minus something to get its partner, cosine and sine are complementary functions, they're linked. Who do you think cotan's complementary friend is? Tan. Who do you think cosecant's complementary friend is? No, that's its reciprocal friend. Cosecant goes with secant. And then mirror it. Who would sine also friend up with in reverse? Cosine. Who would tan friend up with in reverse? Cotangent. Starting today, these arguments start to matter. A lot of you guys on your, well, no, I can't say a lot of you guys, there's only 4 of you, okay, but sometimes on the test, I was only seeing things like sine, cosine. You need to get a little more on top of, every trig word needs what's called an argument, like sine x or cosine y. There's always some sort of a variable or a number called an argument after every trig word. Those start to matter today a lot. So if you're in the bad habit of just writing sine and not sine x, you need to break that habit. After every trig word, there's got to be an argument of some sort. For the last one, I'm going to mix it up a smidge, and I'm going to throw in an x. What does that mean to us from our history together when I start throwing x's instead of thetas at you? It's radian time. So instead of 90, who would be the radian equivalent of 90? No, pi is 180. Pi over 2. So on any of these properties, when you do it from memory, I don't care which one you do, but on one of them, throw a radian in. On one of them, throw a degree in. And on the rest of them, just do your favorite thing, which is probably degrees. But I want to see at least one 90 minus theta to make a theta, at least one pi over 2 minus x to make an x. Who is secant's friend in reverse? Cosecant. So there's 6. We sort of knew that already. Question about those 6? And here's 6 more. You don't know anything about these. These you'll just take by faith. I don't, maybe I could, but I don't want to explain why these work. What these look like is they look like distributing problems. These aren't distributing problems. There's no such thing as distributing the arguments of a trig word. That's not a thing. So we just memorize it and trust me. But cosine, if the argument has a subtract problem, the cosine property is going to go cosine, cosine, then sine, sine, and just go in the order of the letters they gave you. I went A then B, so you could go A then B, A then B. But you have to remember to switch up the sign. If cosine is subtracting, we're going to go with an add. And it's going to take a little bit of time, energy, effort to get this one memorized. The good news is if you memorize the subtracting version and want to do the adding version is the exact same thing, just flip the sign. Question on that? Sine's going to go different. Sine has a little bit more of a scramble to it. Cosine kept the cosines together, kept the sines together, not a big fuss. Sine is a little bit more mixed. So sine, we're going to go sine, cosine, cosine, sine. A little more scramble. What I do on this one, this little memory trick, since there's more of a scramble of the words, I don't need to scramble the sign. So sine, subtract is going to make a subtract, unlike cosine. Cosine had less scrambling of the words, so the subtract scrambles into an add. It's going to take some energy to memorize that. But the good news is, if you get that one done, when we switch the sign, just switch the sign. We're good. Tan of A minus B, we're going to go fraction. On top, it's tan A minus tan B. The bottom's 1 plus tan A tan B. And if you get that one memorized, the other one just switch signs. So there's 6 of those. Whether you call them sum and difference or composite, there's a 6. So there's a 14-point quiz to start our new grade period of grades. We'll do the book cover today too once I'm done with doing this. I'm not going to interrupt to do that right now. But so we'll start off with an A+ book cover hopefully, and then a 14-point next time talk briefly.
Yeah. On the paper it says 6, is that the like plus and minus or 3?
Yeah, the subtract version is one, then the add version is another. I would not bother rewriting the whole thing. It's the same property, just the sign switches. So if you write them the same way I wrote them, this is like 1, 2, 3, 4, 5, 6. Anybody else? Something about that? So. Homework off of this is going to end up being 84. We're going to work from 21 to 38. So this whole thing, you could either look at it as one problem or 6 problems. Okay? In the book, it's going to be 6 problems. 21, 2, 3, 4, 5, 6 are going to be a process like this. But it's sort of one problem. This all like goes together. So I'll do this whole process. That is going to be a process you'll try to duplicate on 21 to 26. So Oscar and his heap of apples is back. So what they're going to do is describe to you a situation that's going to let you draw a right triangle, Oscar having a heap of apples kind of picture. So they're saying to you that sine of A is 2/3, which is positive. Cosine of A, by the way, is greater than 0, also positive. So I need to draw into which quadrant if they're both positive? Quadrant 1. When we've made our Oscar and his heap of apple pictures, we've always then drawn to the x-axis. Right angle. This is called a reference angle. It always touches the x-axis. Relative to the reference angle, this side is OA or H. That is O, H, A. If the sine is 2/3, who's the 2? The O. Who's the 3? H. So how can we figure out the A? Close? Square subtract root to get a length. Square subtract root, that's the root of 5. Question about that. What we're going to need to know from this in the long run is what the sine of A is and what the cosine of A is. Peeking at this picture, what is the sine of A? 2/3. It better be 2/3 because we knew that to start. Okay, so if you drew this whole thing and you come out with a sign that's not 2/3 anymore, you need to re-examine your drawing because you did not help yourself. Cosine of A is new news. What is the cosine of A? Root 5 over 3. Question about the A part of the world? We step into the B part of the world. In the B part of the world, I'm telling you tan is 4/3 positive, but sine is under 0. Sine is negative. Where can we go that tan's positive but sine's not? Quadrant 3. So here we go. Always then triangle to the x-axis. Reference angle touches x-axis. This would be OA or H? O. So 4, 3 or mystery? 4. This is H. Don't know that one? So that's got to be a 3. Why is my picture wrong or incomplete, depending on which adjective you prefer? 4 should be a negative because it went down. 3 should be a negative because it went left. And then negative dividing negative does indeed turn back into a positive. The whole reason we do this is to identify the sine of B, which is news, and the cosine of B, which is news. What is the sine of B? Well, first I need the hypotenuse. 3, 4, 5. So sine, negative 4/5. Cosine, negative 3/5. That's a lot of work. We don't have any answers yet, but now the answers will flow freely. Question about any of that picture drawing? Am I okay on screen that whole thing appeared? Can you tell, including to like my hand? So now we're going to use the properties over there. If we had a cameraman, we'd swing the camera and look at the properties over there and swing back, but you know, you can just use your imagination. So if we're going to do cosine of A minus B, we're just going to use the property from over there, but we're going to fill in the blanks. The cosine A minus B property from number 1 over there starts off with cosine of A. For the duration of this problem's existence, cosine of A is root 5 over 3 times. We'll grab cosine of B, which is negative 3/5. Sine, plus or minus? Plus. Grab another fraction. The property says to grab sine of A, 2/3, times, grab the sine of B, negative 4/5, and then we're going to try to make that better. Question about how we essentially filled in the blanks with those. If we multiply these, and if we multiply those, we're adding fractions. Adding subtractions are supposed to have a common denominator. Will they naturally? Yeah, they're both going to be who on the bottom? 15. I think that's always going to happen. It'll just naturally have that common denominator. Negative 4 times 2, I'll splotch a minus 8 at the end of that. What's the best way to write this? Negative 3 root 5. Numbers that aren't rooted can't multiply numbers that are rooted. And that is our answer. Question there. So there's answer 1. It was a lot easier to get answer 1 than to build all those pictures. The answers, like I said, will flow a little quickly now. If I go plus, what's the only difference if I go plus? This is a minus, and then negative times negative is positive. So there's 2 answers. If you blinked, you missed that one. That one went fast.
So do you have to do the negative and the positive every time you...
They're going to do all 6.
Oh.
So the same thing will happen on a test. On a test, I'm going to have you draw an A picture, draw a B picture, and then on the test I'll be asking you to do about 15 problems off of those 2 pictures. In this homework, we'll draw the 2 pictures, we're going to do 6 answers from it. So from there. Now let's go sine. So sine, we'll grab our fractions. So it's going to be fraction times fraction. That property has a minus. Fraction times fraction. So if we grab the right fraction answer, who are we grabbing first? 2/3. Who's next? Negative 3/5. Who's next? And then the only fraction we didn't use yet is negative 4/5. Again, the common denominator of 15 just happens naturally. If you don't have the same bottom on all of these answers for the first 4, something bad has happened. Multiply these, that's negative 6. When we work all of this out, total off of this back half. Close? Positive. We got 2 negatives in the mix, so we're going to be an add for root 5. Something there. If I switch it up to a plus, you would make that a plus, which makes this minus. 4 down, 2 to go. Here's a temptation you want to fight off. Most of the time you can't reduce. It might be tempting to you to reduce 3's with 15's, because 3's do reduce with 15's. But you have to triple play reduce it. You have to hit all 3 numbers. So 3 and 5, or 3 and 15 you can divide by 3. But 8 can't, so you can't touch it. If this 8 were a 9, then yeah, you'd hit all of those numbers. If all of the numbers can mutually divide by something, you'd do it. Here, same thing. 6 and 15, you could divide by 3, but 4 won't play nicely with its friends, so you just leave it alone. But if this 4 were something that 3 could also go into, you'd hit them. Question about that. tan. We could use the property over there. I don't want to, because if we did, you'd end up with fraction minus fraction on top of 1 minus fraction times fraction. Fractions inside a fraction is a thing we handled in Algebra 2. Like, it can be done. No one wants to, so we're not going to do that. What's a previous way you've learned that you can make tan answers anytime you want using old ideas from this chapter? How can you do tan stuff? Sine dividing cosine. If we're going to take sine stuff, divide by cosine stuff, we can make tan stuff. I'm going to skip the minus answer for a second and do the plus answer, because the plus answer is what I have showing. So if I take sine's answer that's in the box and divide by cosine's answer that's in the box, what happens when you divide fractions? They flip. So if this divides this, and that makes that one flip, who can cancel? 15s. That should always happen. We already said those are going to always have all the same bottoms, the 15s match. So when we go to make tan stuff, the 15s should always cancel. You're just going to need to put sine's top over cosine's top. And then we're going to have a little bit of an algebra remember way. Where we're going to go next isn't, I wouldn't say easy, but it's easier than if you had fractions inside of fractions, with some of those fractions having roots in them. Question about how we set that up to get started? Okay, why does the math community criticize this? Roots on the bottom. How do we fix roots on the bottom? Multiply by something close to itself. Conjugate's going to come into play. If it was just on top of the 3 root 5, we'd multiply by a root 5. We wouldn't worry about the 3, because 3 is okay. But we'd multiply by root 5 if that's all we had. But if there's adding or subtracting, we're going to have to go conjugate. So we're going to go negative 3 root 5 minus 8, negative 3 root 5 minus 8, a little bit of foiling activity. But you're going to catch some breaks, because every time a root 5 multiplies another root 5, that's just going to be 5. We'll do the bottom first, because the bottom's going to be a little bit easier. Negative times negative is 3 times 3 is 9. Root 5 times root 5. Regular 5, regular 9 conspire to make 45. I don't care what this makes, and I don't care what that makes, because what's going to happen with them? They cancel out, so who cares? The 8s will make 64. 45 minus 64 is negative 19. That's a new bottom compared to everything else. That's okay, that's going to happen. The chances of this being anything to do with 15s anymore is practically 0. There. This will make how much? 18 root 5s. This will make 32 root 5s. I'm not going to write those down because I'm a little cramped for board space. If you need that, write that in your own notes. But there's an 18 root 5 and a 32 root 5. Put them together, what's that going to make? 50 root 5. Then we need to do these. Positive 48. These. Get 12 times the root 5s will make 5. 12 times 5, and that'll make the 60 that we heard. So 12 times 5, we got a 60 there. So 60 and 48, that's 180. It's worth a brief thought. Can anything go into all three of these numbers? That answer will be no almost every time. Occasionally yes, but most of the time no. If I wanted to do the minus version, which I don't in the interest of time, I would have used the answers that I had changed. Like whatever these were boxed before I changed them, I'd have had that very similar problem. I think the only difference is going to end up being one of the signs will be different. I there's going to be a major difference in there. Question about that? Okay, then, so that handles 21 to 26. Here is 27 free of charge. So 27 to 32 are going to be like what I'm about to do there, but I'm going to have to do a small camera turn. I'll do myself walking over a wire. So 27's directions are talking about exact values. Exact values is code for leave your calculators at home, use your chart. Okay. So with 15, the first thing we're trying to do is come up with some math way using these numbers from your chart. Somehow use those numbers to create a math problem that 15 is the answer to it. What's a way we can use these numbers to make a problem that'll create a 15? 60 minus 45 is fine. 45 minus 30 would have also been acceptable. There's different ways that that could have been done, but we just need some problem that can make a 15. Now we're going to use the subtracting property from a second ago. But we don't have an A, we have a 60. And we don't have a B, we have 45. So instead of cosine, cosine, sine, sine with A's and B's, I've got 60s and 45s. And the sign on that is an F. Question about how I blasted that one thing out into like a quadruple trig problem. Just use the property. Now look these up on the chart. Cosine 60, I gave you the thing with the chart. What is that? That's a half. Cosine of 45, 2 over 2. Sine 60, 3 over 2. Sine 45, 2 over 2. We're adding, and there's fraction stuff. As always, we'd like to have a common denominator, do we, naturally? Yeah, you almost always will. Maybe always will. Common denominator in both fraction worlds is 4. The multiplication of this piece of the world is root 2. This piece of the world, root 6, and then don't fall into the trap of trying to divide these all by 2. This is not the same type of number. Roots can't divide regular old numbers. So root 2 plus root 6 divided by 4, that's the best you could do. Question about that? One of the questions in this section I think will ask you to do secant of 15. You don't have to start from scratch. If we already built cosine of 15, what's the simplest way to build secant of 15? Flip it. Just take the answer you already made and flip it. Don't start over. Secant of 15 is this upside down. So we're going to use a combination of like old and new properties to do this group from 27 to 32, but there's 27 for free. The next group, they want you to do stuff with 75s. I'm not going to do one of those free of charge other than to say, how could we do the math problem here to produce a 75? 45 plus 30. That would work, and then we could do stuff with that. That's not what that problem was, so just I'll erase that for now. But from 27 to 38, there's ways to use all of the properties in conjunction with your chart to make answers. There's some easier roads and some harder roads. Question about 27 to group the 38. Okay. Then 39, they say find a decimal approximation. So here's 39, free of charge. Decimal approximation usually makes you kind of happy. That means turn your calculator on. So they say find this decimal approximation 2 ways. A, evaluate the answers that you just got. So if you grab your calculator and you punch in root 2 plus root 6, hit enter, divide by 4, hit enter, Somebody do that and see what it says. 1.4. A little less than 1 maybe. Then root 2 plus root 6, hit enter, divide by 4. I'm feeling like it's a decimal close to 1, but not quite. I might be wrong. 2.6. What did I do?
Maybe I clicked it on. It might be like.
Yeah, I don't think that's right. Try root 2, hit, root 2 plus root 6. Like root 2, close the parentheses.
Yeah, I didn't close it.
Yeah, root 2, cut that off, plus root 6, cut that off. Hit enter, divide by 4.
0.965.
All right. Question about where we pulled that from. Then they say B, use a calculator directly. That means just punch cosine 15. If you just push cosine 15, it should show you up to 0.965 also. And then you have a lot of confidence that you are right. So those are the same. If this didn't come up 0.965, what's probably your mistake on B when you punch in radian mode? We need to be back to degree mode. Okay, so with 15s and stuff, we're in degree mode again. So if you punch cosine 15 and you don't get 0.965, check your mode. It should be. Those should agree with each other. So 39 to 44 is just pushing some buttons to verify that what you were doing earlier was the right stuff to do. Question about any of that? Yeah.
How did you do that in your head so fast?
I know root 2 is 1.4. It's 1.414 because I took trig in a day before calculators were super prevalent, and our teacher made us memorize some of the root 2, like root 2 and root 3. Root 3 is 1.732. He just made us memorize that. Root 6, I tried to just like, I know 25 squared is 625. I know that, so that makes this easier. In other words, if I rooted 6.25, it would be 2.5. So I'm thinking root 6 is a little less. I'm thinking that's 2.4-ish. So I got 2.4 and 1.4 is somewhere in the neighborhood of 3.8 total, dividing 4. I'm close to 1, but a little under.
That was cool.
You like that trick?
Yeah, the second one.
That's a good trick. Yeah, I just tried to think of what squares I knew that could get me into an area that was like a 6 or a 600 or something like that. So 2.4 is 576, and 2.5 would be 625. So I'm like in there somewhere. 2.45 probably. There's my tricks for you. It's not magic, it's just there's a lot of numbers I've memorized either on accident or on purpose. A lot of the squares, I know a lot of squares because you do this all day long squaring a lot of different numbers, like 35 squared is 1225. I'm not doing that in my head, that's just, it's like I know that like I know my phone number, it's just a thing that I know. Anything else? No, I take that back. I'm amazing. A lot of it's memory.